Hi students, this is our 6th lesson for the topic of differentiation for the International Baccalaureate course Analysis and Approaches, and this lesson is appropriate for high level and standard level students. In this lesson we're going to cover the properties of curves. So recall, to find the gradient of the tangent to the curve f of x is equal to 3x cubed take away 9x at the point 1, -6, first, we differentiate, so f dashed of x is 9x squared take away 9, and then we substitute in x is equal to 1. So f dashed of 1 is equal to 9 take away 9, which is 0. So the gradient of the tangent to f of x at 1, -6 is 0. The tangent is flat. In other words, in that particular instance, y isn't changing at all. We can also find the equation of a tangent. Let's find the equation of the tangent to the curve f of x equals 4x squared plus 2x minus 9 at x equals -1. We'll start by differentiating. F dashed of x is equal to 8x plus 2, and we'll substitute in -1 for x. So the gradient of our tangent is -6. Now we're going to use the point gradient formula, which means we have the gradient, but we need a point. We've only got x is equal to -1, we need to find the y coordinate, and we find that by substituting -1 back into the curve. So f of -1 is equal to -7. Now let's substitute into our formula. We have y take away -7 is equal to -6 multiplied by x take away -1. Tidying that up, we have y is equal to -6x take away 13. Now in a previous video we looked at how to use the graphics display calculator to calculate the derivative. Now as part of exam conditions you can't use a graphics calculator that will calculate the derivative in terms of x. So you have to have that feature turned off. But you can use it to calculate the derivative at a particular point and to show the equation of the tangent. So let's just revise. Let's find the gradient of the tangent to the curve f of x equals 4x squared plus 2x minus 9 at x is equal to -1. We open a normal calculator page and go to Menu, Calculus, Numerical Derivative at a point. And we're going to put that point in, or the x value, which is -1, and choose the first derivative. And when we get the screen up, we just type our function in here. And so the gradient at x is equal to -1 is -6. Now to find the equation of the tangent, we do it graphically. So what we're going to do is open a graph page and graph the curve, which you can see there. Then we go to Menu, Geometry, Points and Lines, and Tangents. And click anywhere on the curve and then type an open bracket and put in your x coordinate and then enter. Let's go through that more slowly. So here I have the TI Inspire CX, and I've opened a graph page and I've graphed the curve. So to work out the equation of the tangent, then what we do is go to Menu and then Geometry, Points and Lines, and Tangent. Now as I'm hovering over that curve, you can see it's quite difficult to get an exact x coordinate. So just click anywhere and then open a bracket and type in the x coordinate you want, which in this case is 1. And when you hit enter, you end up with the tangent and its equation drawn on the graph. Okay, let's move on. The normal is the name of the line that is perpendicular to the tangent at a particular point. Now finding the equation of the normal is pretty simple. It's just an extra step. Find the equation of the normal at the point 1, 10 to the curve y equals 4x to the power of -1 plus 6x. Again, we're going to start by finding the derivative, which is -4x to the power of -2 plus 6. Now we need to work out the gradient of the tangent first, so we're going to substitute in x is equal to 1. So at x equals 1, y dash is equal to -4 plus 6, which is 2. So that's the gradient of the tangent. Now the normal is going to be perpendicular to that, so we need to do the negative reciprocal. So m is going to be equal to -1/2. And now we're just going to proceed as we would for the tangent. Y minus y1 is equal to m brackets x minus x1, substituting in, and then we need to tidy that up. So what we can do here is get rid of this fraction by multiplying everything by 2. Gives us 2y minus 20 is equal to negative x plus 1, and making x positive, we have x plus 2y minus 21 is equal to 0. Now on the calculator, it's a little bit more complicated. Again, we're going to do it graphically. So we go into a new page and graph the curve, and we add the tangent like we did before. We go to Menu, Geometry, and we're going to construct a perpendicular. And we've got to click on that point 1, 0 so that it goes through that point. Now if we want to get the equation, then we go to Menu, Coordinates and Equations, and we click on the normal line. Let's have a look at how that works in practice. This is where we were when we finished the last question, and we worked out the gradient and the equation of the tangent. Now, to draw the normal, what we've got to do is go to Menu, and we're going to go to Geometry again, but this time to Construction and then Perpendicular. And we've got to tell it where we want that perpendicular drawn, so we click on that point. Now we need to get the equation of that line, so go to Menu, go to Actions, and go to Coordinates and Equations. So we want to find the equation of that line, so click on that line, and now we have the tangent and its equation and the normal and its equation. Okay, let's look at some of the properties of the first derivative. Recall, the first derivative is the gradient of the tangent to the curve y is equal to f of x. It is called the gradient function. And remember from year 7 or year 8, if we have a straight line that's going uphill, the gradient is positive. If it's going downhill, the gradient is negative. If it is flat or horizontal, the gradient is 0. And if it is vertical, it is undefined. Now we can use that information to determine whether a function is increasing or decreasing or stationary. And here's the rule. If the first derivative is greater than 0 for a particular domain, the function is said to be increasing. And you can see a couple of tangents I've drawn to the curve there. They're all going uphill, so we have a positive gradient. So the function is increasing at this point. If f dash of x is less than 0 for a particular domain, the function is said to be decreasing. And here you can see it's all going downhill. And then finally the last part of the curve there, we're going uphill again. So we have got increasing at this point, decreasing here, and then increasing again. Here's an example. Show that the function f of x is equal to 3x plus 5 is increasing for all real numbers x. Now this is called monotonic increasing, which means always. So we find the derivative, which is equal to 3, and since 3 is always greater than or equal to 0, f of x is monotonic increasing for all real numbers x. Let's try a harder example. Find the interval or intervals where f of x is equal to x to the power of 4 minus 4x cubed plus 5 is decreasing. So again, we're going to start with the first derivative, which is pretty straightforward. F dashed of x is 4x cubed minus 12x squared. And we want to find when this is less than 0. So factorize, we need to solve an inequality. And we're just going to use a sign diagram. The critical points here are 0 and 3. Let's test a point here, negative 1. Now remember, you don't need to work all of this out. You can just substitute the negative 1 in there and decide if this is positive or negative. So that's positive, and put the negative 1 in here, we get a negative. So positive times a negative is a negative. Now let's test x is equal to 1. We have a positive times a negative is also a negative. And now let's test x is equal to 4 we have got a positive times a positive, which is a positive. So it's going to be decreasing here and here, but not at x equals 0, because at that point it's equal to 0. So f of x is decreasing for x is less than 0, and for 0 is less than x is less than 3. Now we've talked about increasing and decreasing functions, but if the gradient of the tangent at a particular point is 0, then the curve is said to be stationary. There are two types of stationary points. There's a turning point, we also call those a maximum or a minimum, and there's a stationary inflection, and that means the curve is stationary but it's changing its concavity. Now here's some new terms for you. This is concave down on the left, and this one is concave up. And so this stationary inflection might look like this. So it's coming through here, it's stopped at this point, but it's changing from concave down to concave up. So that one there is a stationary inflection. So let's have a little chat about maxima and minima. A function can have a global maximum or minimum, but we can also have a local maximum or minimum. Those are those turning points. So the global max or min is the highest or lowest point that the function attains. And in this case here, the highest point is at 2, 3, and so the global maximum is 3. That's the highest it gets. Here we have a local maximum. Here's a local minimum, and this particular function has no global minimum because it goes off to negative infinity. Let's identify the stationary points on this graph. We have a local maximum here. We have a stationary inflection here. And we have a local minimum here. There is no global maximum nor a global minimum. Here's an example. Find the stationary points for f of x is equal to x to the power of 4 minus 2x squared. So we differentiate and we solve 4x multiplied by x squared minus 1 equals 0. So x is equal to 0 or plus or minus 1. Now it asks us to find the stationary points, so we also need the y-coordinates. And the way to get those is to substitute these points back into the curve. So we have stationary points at 0, 0, 1, negative 1, and negative 1, negative 1. Pretty easy to find the coordinates of those turning points, but we never figured out whether they were maximums or minimums. And one easy way to do that is to use the second derivative. The second derivative, f double dashed of x, finds the gradient of the tangent of the first derivative. In other words, how much is f dashed of x changing as x changes? Now, if f double dashed of x is greater than 0, then the curve y equals f dashed of x is increasing, and this will mean that it is concave up. If f double dashed of x is less than 0, then the curve y equals f dashed of x is decreasing, and this is concave down. And if f double dashed of x is equal to 0, then the curve y equals f dashed of x is stationary. This is an inflection or a change in concavity. We can get just a simple change like this going from concave down to concave up, or we can get one of those stationary inflections that I was talking about before. So here's example 1. For the curve, complete the table indicating whether f of x, f dashed of x, and f double dashed of x are positive, negative, or 0 in value. Now, f of x is just the y-coordinate. So this is pretty easy. We're just going through deciding whether the y is negative, 0, or positive. So pretty easy. F dashed of x is the gradient of the tangent. Is the curve increasing, decreasing, or stationary? So increasing here, stationary, decreasing, stationary, increasing. And then finally, f double dashed of x is concavity. We can see this curve is concave down here, changes at this point, and then concave up here. So it's going to be negative, negative, negative for concave down, 0 at D because we change concavity, and then positive, positive, positive. Which brings us to a really important part of the course, curve sketching. Sketch the curve f dashed of x equals x cubed minus 3x squared plus 5 by finding the stationary point or points and inflections. Start as we always do by differentiating, and then solve 3x squared minus 6x is equal to 0. So just factorising, x is equal to 0 or 2. And so that means we have stationary points at 0, 5 and 2, 1. Remember, you just substitute the 0 back into the curve to get the y coordinate. We need to figure out whether those are maximums or minimums, so we need the second derivative. So f double dashed of x is equal to 6x minus 6. What we're going to do is substitute the x coordinate into here. If it's greater than 0, then it is concave up. If it is less than 0, it's concave down. So let's start with x is equal to 0. F double dashed of 0 is equal to negative 6, which is less than 0, therefore it is concave down. Concave down is a maximum. Now let's do x is equal to 2. F double dashed of 2 is 12, take away 6, which is 6. Greater than 0, concave up, it's a minimum. Now all I need to do is find any inflections by solving f double dashed of x is equal to 0. 6x minus 6 is equal to 0, x is equal to 1, so there is an inflection at 1, 3. And remember, the way to find the y coordinate is to substitute back into the curve. And then when you sketch your curve, do a large sketch, so 1/3 to 1/2 of a page. Use a ruler and make sure your scales and your axes are consistent. And also identify all the critical points that you found. So here we've got a maximum at 0, 5, an inflection at 1, 3, and a minimum at 2, 1. Put arrows on the ends of your curves and label your axes y and x. Now we've talked about stationary inflections before. They occur when the first and the second derivatives are equal to 0. So let's find and classify the stationary points for y is equal to x cubed multiplied by 4 minus x. We need to expand that out first and then differentiate. And so we want to solve 4x squared multiplied by 3 minus x is equal to 0. And so stationary points are going to occur at x is equal to 0 and 3. And to find the y coordinates, we substitute each of these x coordinates back into the curve. And so we have stationary points at 0, 0 and 3, 27. Now let's work out the second derivative. It's equal to 24x minus 12x squared. And so when x is equal to 0, we have our second derivative also equal to 0. So therefore this is a possible stationary inflection. We'll talk more about this in a second. At x equals 3, the second derivative is equal to 72, take away 108, which is negative 36, less than 0, concave down, therefore it is a maximum. Now there are occasions when the second derivative test doesn't work. Let's find and classify the turning point or points of y equals 2x to the power of 4 minus 5. So we'll differentiate, we get 8x cubed. And we're going to put that equal to 0. And obviously x is equal to 0. So there's a stationary point of some description at 0, negative 5. The second derivative is 24x to the power of 2. And when we substitute 0 in there, we get our second derivative equal to 0, which suggests a stationary inflection. But it isn't. It's a minimum. So what we're going to do is test the first derivative on either side and then just draw a rough sketch. So our first derivative is 8x cubed. We knew we had a stationary point at x is equal to 0, so I'm going to test negative 1, 0 and 1. So substituting into here, when x is equal to negative 1, the first derivative is negative 8. When we put 0 in, we get 0. And when I put 1 in, I get positive 8. And a quick sketch, negative slope, stationary, positive slope. It's a minimum. For this reason, if the first and second derivatives are 0, apply the first derivative test to check your results. So let's return to that question that we just looked at. We had to find and classify the stationary points for y is equal to x cubed multiplied by 4 minus x. We found 2 stationary points. At 327 there was a maximum, and at 0, 0 there was a possible stationary inflection. Now this one here is a maximum, so we don't need to worry about it. But whenever our first and second derivatives are equal to 0, we should double check. And we're going to use the first derivative test. So we're going to substitute in either side of x is equal to 0. So let's just draw up a little table. We want -1, 0, and 1. Substituting -1 in here, we end up with 12 plus 4, so it's positive. Substituting 0 in, we know we get 0. And substituting 1 in, we get 12 take away 4, which is also positive. And just a quick sketch, positive, 0, positive, it is a stationary inflection. Now, last thing for this lesson, we need to know how to sketch the derivatives and the antiderivatives of curves. So here we've got a curve y equals f of x, and we want to sketch the first derivative and the second derivative. Now, sketching the first derivative is pretty easy. We're looking at the gradient of the tangent. So this section here, it's positive because it's going uphill. Here it is equal to 0. Here it is negative because it's going downhill. Here it is equal to 0. And here it is going uphill. And so we want to draw something positive, something going through 0, something negative, something going through 0, and something positive. So something like this. And to sketch the second derivative, we're going to do exactly the same thing, but this time to the first derivative. So here we can see it's going downhill, so it's going to be negative. Here it is 0, and here it is going uphill, so it's going to be positive. So we want something negative, something going through 0, and something positive. So it'll look something like that. Now, if we want to sketch the antiderivative, it's much, much harder. I know we haven't covered antiderivatives, but I think you can follow this. This is the graph of the derivative, f dashed of x, of a particular curve y is equal to f of x. And we want to draw a possible sketch of y is equal to f of x. Now, what's important here is the sign of this curve. So here we've got positive, here it is 0, here it is negative all through here. Here it is 0, and here it is positive. So that means our original curve was increasing here, decreasing here and here, and increasing here. And it was stationary at these 2 points. All right, let's see if we can draw it. It's a good color, purple. So it's increasing, stationary, decreasing, decreasing, stationary, increasing. So it's going to look something like this. Increasing, stationary, decreasing, stationary, increasing. Now, I don't know where on the y-axis that curve is going to be, but roughly we have got a turning point here, then we've got a change in concavity here, and then another turning point here, and then increases. Okay, let's finish off with a past paper question. So this is from May 2024. It's paper 2, so it's a calculator question, and it's question 9, so it's pretty tricky. And it's 8 marks. Consider the curve y is equal to x minus 4 all over ax squared plus bx plus c. A, b, and c are non-zero constants. The curve has a local minimum point at 2, 1 and a vertical asymptote with equation x is equal to 1. Find the values of a, b and c. All right, at first glance, I think we're going to end up with a system of linear equations that we'll solve on the graphics calculator. I've got a couple of things that we can do. If we differentiate this thing and put it equal to 0, then we will get some information. We also know that 2, 1 lies on this curve, so we can substitute that in. And we need to do something about this vertical asymptote. And I'm actually going to start here. If there's a vertical asymptote with equation x is equal to 1, then when x is equal to 1, that denominator is going to be equal to 0. So that's a pretty easy thing. A plus b plus c must be equal to 0. Okay, I've just substituted 1 in where x is. Now let's substitute 2, 1 into the curve, and we will end up with a second equation, 4a plus 2b plus c is equal to -2. And finally, we know that the derivative of this, when x is equal to 2, that derivative will be equal to 0. So to differentiate this, we have a quotient rule. U is equal to x minus 4, v is equal to ax squared plus bx plus c, u dashed is 1, v dashed is 2ax plus b. Constructing the quotient rule, and we know that when x is 2, this whole thing's going to equal 0. And in fact, when I solve this equation equal to 0, this denominator is not important, so I can just ignore that. So substituting 2 in, we end up with 4a plus 2b plus c. Take away, up to here, put in the 2, so -2, and then 4a plus b. And tidying it up, we end up with 12a plus 4b plus c is equal to 0. And so we have 3 equations. And just putting that into the graphics calculator and solving it, we end up with a is equal to 3, b is equal to -11, and c is equal to 8. That's it for this lesson. Our next lesson is on implicit differentiation.